I'm meteorologist Dan Baumgart with the next module on probability of weather type methodologies. We're going to look now at the production of snow and ice accumulation grids, and this is work that Andy, Justin, and myself put together. So the probability of weather type grids allow the total QPF to be divided among the weather types that we expect. So what we do is we take the total QPF, whatever it is, and then we divide it up by the different types depending on how high the probabilities are. So we basically take the whole pie. This might represent the total probabilities out there, and each of the probabilities have different amounts of probability. So we can take the QPF and actually divide it equally, just in a linear way, into the different precipitation types. And so we have a QPF for each amount that's or each type that's out there. So we take the total QPF and divide it up. So how this works kind of in a flow chart is you work on your top-down grids, like the max wet bulb temperature aloft, the probability of refreeze of sleet, and the probability of ice present. You also work on the temperature, dew point, and wind. From all those, we get these probability grids, the probability of weather type grids, and for this case, ice pellets, freezing rain, snow, rain. We might have drizzle in there. We might have some other ones. But for this case example, we have the four probabilities, and then what we do is we take the total QPF and put it into the equation and just linearly figure out the ratio for each of those QPFs, the QPF rain, snow, ice pellets, and freezing rain. And then we just multiply the QPF that comes out for snow by the snow ratio to get the snow amount. We use the ice pellet ratio, which is 2:1 for the QPF for ice pellets. That goes into the snow amount, combines with the snow to give the total snow amount. We take the QPF and partition that out for the QPF for freezing rain. That's thrown through the freezing rain accumulation model, and we end up with an ice accumulation grid. And the QPF for rain is obviously not worked on. But all of the blue that you see in this picture are derived grids, and all you have to do is put the inputs, edit the inputs, and then all of these different grids will fall out automatically. Awesome and internally consistent. So let's take an example of how this works at this grid point, whatever it may be. K, wherever you are, has an inch of precipitable or of QPF in 6 hours. And then we have these different probabilities in your probability of type grids. So 50% probability of sleet, 50% probability of rain, and 100% probability of snow. Again, these are, if precipitation occurs, this is the types that will fall. And so using those different probabilities, we can take that 1 inch and partition it out for the ratio of each of these. So basically here we have 200%, and each of these get divided up into each 25% is a quarter. So anyway, we take the 1 inch and we divide it up by the same ratio of probabilities that you see on the right-hand side here. And so we see the 1 inch is broken down into a quarter inch of QPF for sleet, a quarter inch of QPF liquid equivalent, and a quarter inch of rain, and then 0.50 or a half inch of liquid equivalent for snow. And so using the temperature, snow ratio, and sleet ratio grids, we can come up with a great first guess on snow amount and ice accumulation. In fact, using this at La Crosse, we rarely had to edit these grids once we derived them. So you would go back and edit your probabilities possibly if you didn't like the outcome, but they make some pretty outstanding ice accumulation and snow amount grid that you don't have to edit. So let's dig into this a little bit deeper and just show you a little bit more math on how this works. So in this scenario, let's say we want to increase our probability of sleet here to 100%. It was 50 in the last slide. Our pot rain will stay at 50%, and our probability of snow is going to be 100%. In this case, our QPF is automatically reallocated. So what we do here is we total these up, 250, and then we just take the probability of each over that 250 to figure out a ratio of the total, and then multiply it by the QPF. So the QPF is 1 inch, so we basically take that 100%, 100, and divide it by 250. We get 0.4 in the form of sleet, 0.2 in the form of rain, and 0.40 in liquid equivalent for snow. And those were automatically reallocated because we wanted to put some more sleet into our top-down grid. So you go in, you edit for more sleet in your top-down grids, and then you run the tool. And in the forecast builder, it automatically reallocates the QPF into the proper bins, and then the snow amount and ice accumulation is simply readjusted. So then we just take those liquid QPFs that are linearly created from those ratios, and we multiply them out to get our snow amount grid. For example, here we have 0.40 liquid equivalent of sleet for QPF, and then we multiply it by our 2-to-1 ratio, and we get about 0.8 of sleet. For snow, we have a snow liquid equivalent. Let's just use an example of 12-to-1 here. We multiply that by 0.40, and we get 4.8 inches of snow. We add them both together, and our snow amount grid at K wherever you are is 5.6 inches. This is all derived. You have to do nothing here except start by altering your input using those input grids that we talked about earlier. The beauty of this, again, it's all internally consistent. So when you take QPF out of sleet and put it somewhere else, or you increase the probability of sleet, it will automatically take that QPF out of sleet and put it where you want it. So these, we are internally consistent, and they're derived. You don't have to edit these grids. Let's take another example here where you edit the top-down grids for more sleet and freezing rain. Suddenly your forecast is, you're a little bit colder in the boundary layer, let's say, so your sleet's a little bit more dominant, and you now start to get into this issue of freezing rain now at the surface. So we've now reallocated to 100% probability of sleet and freezing rain. Our rain and snow is very small. So we take that 1 inch of QPF that we started with in this example, and now our total is 220%, as you can see on the right. We just figure out the ratios for each, and then it comes out to 45 hundredths of sleet and freezing rain for liquid QPF for each of those types. No snow QPF, obviously, because of the zero probability there, and 1/10 of an inch of rain. And then the snow amount and ice accumulation will readjust to that. So let's see how it readjusts for this example. Since we don't have any snow, the only thing in the snow amount is going to be our 0.545 liquid equivalent for sleet multiplied by the 2-to-1 ratio, and you get a snow amount grid that is 0.90 for that grid point. For the ice accumulation, it's a little bit different, a little bit more complex. What we do with the freezing rain QPF of 0.45 now is send that to the freezing rain accumulation model. So we need to talk a little bit more about that. So here's a little bit more detail on the freezing rain accumulation model, and by this time you should have gone through that training, that 1.5 hour training from Brian Bargenbrook and Chris Sanders, where they talked about the freezing rain accumulation model. So in our ice accumulations, the NDFD ice accumulation grid and the ice flat accumulation, we are populating the flat ice accumulation into the ice accumulation grids at this time. These are for slightly elevated horizontal surfaces. So they're trying to replicate what we're measuring at the ASOS, because that's the study that Brian and Chris did. So that's has the most direct impact. So that the technique for FRAM uses the wet bulb temperature, the wind speed, and hourly QPF for freezing rain that we have partitioned to produce an hourly ice ratio and finally an hourly ice amount. And we'll go over an example in 1 second here. And then from that flat ice accumulation, we can also derive an ice line accumulation based on the research. So this is ice for radial surfaces like branches and power lines. So we now have data that we can send to our users that help our power companies or what have you kind of get a feel, and us forecasters get a better feel for what the ice accumulation on branches and power lines will be like. And that's about 40% roughly of the ice flat accumulation grid. So here's an example here at K wherever you are. Temperature, dew point, and wet bulb are all 28 degrees, wind speeds at 10 knots. Probability of freezing rain is 50%, and so that gives us a QPF a little bit less than that because we're going to partition that 0.20 into a probability. So let's say our 6-hour QPF for freezing rain was 5 hundredths. That's about 8 thousandths per hour, if you will. And then we have a wind speed factor that's calculated in the FRAM, a wet bulb factor, the frat precipitation rate, an hourly ice ratio that's calculated from the FRAM. And this is all derived. Again, this is all in the background, just done with the tool within seconds. And then we have an hourly ice, flat ice accretion rate. So in the bottom line here, when you run through your 6-hour ice accumulation for this scenario, your ice accumulation comes out to be 0.08 hundredths of an inch, actually a little bit more than your 5 hundredths of QPF that went in. And in this case, the line ice accumulation is 0.03. So in this case scenario, we see that our ice accumulation is automatically derived, and there's a bunch of different factors that go into it. But you should just at least know that the temperature, dew point, and wet bulb temperature do go into the ice accumulation. And there's also a scenario that covers this situation when you have temperatures in the 30s and you change your wet bulb temperature via the dew point editing, so that you need to be aware of. So that'll be in a follow-up scenario. So that concludes this production of snow and ice accumulation grids brief tour here. The biggest thing again from this is that they're internally consistent. The QPF is always moved around and consistent with your probability grids. And the second point is that they're all derived. There's no human input here. All you have to do is edit your top-down grids and the snow and ice accumulation drop out.